Hi, can you hear me?
Yes, we were checking it turns out the in-room audio, hi Mo, yes, we could hear you. The in-room audio was having a problem. They have now fixed that. We can see people coming in, so we'll wait a few minutes to let people get into the room and then get started. And for those in the room, Tom Hill is at the front of the room because all of your chairs and your working group secretary are all remote. So we asked Tom to sit in front to help us with room issues like the in-room audio volume problem we just got fixed. And Meet Echo has fixed that problem.
Can I just check you can hear me from here, okay?
Yes.
This all going? I'm quiet.
You're good.
Mr. Meet Echo Tech, can you hear me okay? Is it good? Level good? Yeah, okay. Good, good. What? I can't hear anything.
So I guess it's about time if you can get you prepared and go to your room. We have a full agenda. So this is the spring working group meeting, last one. Not last meeting for spring, but last meeting for the week. Next slide. Yes. This is the Notwell. So you are contributing to the IETF. You have to follow the rules and policies. And this slide summarizes those policies, so you should read it. Since we are last meeting for the week, I'm going to assume that you had time to look at it, but it's important. This is our agenda. It's pretty packed and full. So speakers, please limit yourself to your allocated time, which includes presentation and discussions. Is there any comments on the agenda? Andrew?
I'm all good with the agenda.
Okay, you had your mic. In terms of meeting, as you see, all chairs are remote. And thank you, Tom Hill, for helping with the room management. As a reminder, minutes are collaborative, so you can click on the URL and please check your name and your statement. In terms of queue management, it's a bit different this week. So if you are remote, you enter the queue by pressing the raise hand icon. And if you are in Vienna, you have to use the Meet Echo Lite client, I believe. Now, when speaking, if you're remote, you need to separately send your audio. And if you're in the room, you can use the room microphone. And finally, as a reminder, sessions are recorded, both audio and video. Next, please. So you probably know by now, so NumCom has finished, and we have a new ISG. As far as routing area is concerned, Andrew is a new AD, and Martin is leaving. This has an impact for Spring, because Spring Working Group has been assigned to Andrew. So we'd like to welcome Andrew on board. He will have a 5-minute slot to present himself. So I won't say anything. And Martin is leaving. I'd like to thank Martin very much for the 4 years of services. There is no way I can speak as good as Alvaro said during the routing area plenary. So please refer to Alvaro's statement. But again, thank you, Martin. It was a big working group and difficult one. In terms of document, we made some progress on the compressed SRv6 segment list encoding in SRH. So we were waiting for a draft dealing with the relationship between CSEED and RC 4291. It is now published. It's from Suresh. It has been presented in 6 months this week. So you can refer to the presentation. As a consequence, the Spring draft has been posted a year ago. There is an issue tracker initiated. So you're welcome to directly modify it. But if you do, please copy the Spring mailing list for any modifications that you do. As a reminder, the document is now a working document. It is owned by the working group. And so authors, please work with working group to progress on the points raised during adoption. And I think we have a 01 addressing some comments. So thank you to François. In terms of adoption call, we did the call on SRT pass midpoint for restoration. There is a support for the requirement to protect traffic sent in SR policies. There is no support for the two proposed IGP extensions. So document is currently not adopted in its current form. So others are suggested to keep the work on the mailing list. Next. Next slide, please. Joël. Next slide, please. We submitted two documents to ISG for publication. One is pass segment in the MPLS network, and one is integration of NSH on segment routing for service function sharing. I assume those two documents will be handled by Andrew. Next one. Next slide, please. We have the segment routing policy architecture, which is under ISG processing. Actually, I think it has been accepted 1 or 2 days ago. So good. Thank you for the work, everyone. It was a big document. Next slide. No new document in RC editor. And I think that's it. Next on the agenda, we have a slot for the new ID, Andrew. You're welcome to say a word and present yourself.
Andrew, we're not hearing you. You must have muted yourself.
Can you hear me now?
Yes, thank you.
There we go. Sorry, I got a microphone giving problems. I was just saying, firstly, thanks very much for the welcome. And, you know, coming into this working group and having observed this working group for a long time, I think that one of the things that as we work together that I'd like to see in the working group is that we focus on the technical content, potentially lower the heat, because I don't think anybody will deny that at times it has gotten heated. But I would say that it's produced a lot of really good work. And if we work together, focus on the technical, mind the code of conduct, well, the guidelines for conduct, should I say, I think we'll get on well. I've got a couple of ideas as well that I'll be discussing with the working group chairs about things that can potentially smooth things out, and we'll see how it goes. But I'm very happy to be here, and please always feel that my email box is always open, my door is always open. You know, feel free to talk to me about any concerns or issues you've got, and yeah, communication's key. So I'm looking forward to the time together and doing some good work. And that's me. And welcome to take any questions as well.
Thomas, it's up to you for export of segment routing IPv6 information. Sorry.
Thank you very much. Export of segment routing IPv6 information. IPv6. Next slide, please. Before starting into IPv6, I would like to give some outlook in how MPLS and MPLS segment routing is currently being covered in IPv6. Segment routing can be leveraged in MPLS and the IPv6 data plane. In MPLS, the MPLS top label stack section is encoded in the IPv6 entity 7, while the subsequent label stack is decomposed separately in IPv6 entity 71 to 79. So in each IPv6 entity, we have the label, the experimental bits, and also the bottom of the stack bit. While in IPv6 entity 47, we see the MPLS top label IPv4 address, and in IPv6 entity 46, the MPLS top label type, which is describing from which routing protocol or path computing element the label and the prefix has been coming from. And since this was the only change between MPLS and MPLS segment routing, in RFC 9160, we updated the MPLS top label type registry at IANA. Next slide, please. So in order to gain also the same data plane visibility as we have in MPLS and MPLS segment routing and also in SRv6, we need to do the same in IPv6. So currently, I'm aware of SRv6 already being deployed in network operators network. Some of them already started to do migrations from MPLS to SRv6. And speaking for a network operator, I know that especially during migration phases, data plane visibility is very crucial so that we can actually see to which segment routing ID where traffic is being forwarded or being dropped. So in SRv6, the segment routing header is defined in RFC 8754, section 2. Next slide, please. And we are decomposing that in several IPv6 entities. So in the IPv6 SRH segments left, we see basically where we are in the segment list. In the IPv6 SRH tag and the SRA flags, we are decomposing the tag and the flags field from the SRH. And in the IPv6 SRH segment time, same as in MPLS, we are describing from which routing protocol the segment has been coming from. Then in the IPv6 entity SR section, we are decomposing the entire SRH as a series of n octets, while in SRH segment list section, we are decomposing the segment list as a series of n octets. The IPv6 SR segment and the segment basic list, there we are encoding the segment list as an ordered basic list according to RFC 6313. Next slide, please. So we have two ways of exposing the SID list. So either as a basic list, or as a entire section as an octet array. And also here I'm asking especially the network vendors what makes most sense, if you should support in IPFix both or one over the other. The difference between the two are either the decomposition is being done on the export side or on the data collection side. Next slide, please. Some operational consideration regarding the SRH compression. As you're aware of, basically with the SRH compression, we have a so-called compressed seed container, which is basically still a 128-bit long is a 128-bit long CSID list, and therefore basically the IPv6 SRH segment list does not change. It's still a list of IPv6 SIDs, but it can either contain IPv6 SIDs or a list of CSID container or both. So they are not mutually exclusive. It probably makes sense to add into the draft document a section how basically the IPFix data collection can distinguish between a IPv6 SID list and the list of CSID containers. And from what the authors understood, there probably doesn't make sense to decompose the CSID container into compressed SID in IPFix, but there I'm asking for feedback from the working group. Next slide, please. So far we have been collecting feedback from Sprim, Ops AWG, and IPFix Doctor. So from the feedback, we have included the new IPFix entities for the SRH section and the segment list section, but also added the segments left to expose where in the segment list the forwarding happens, and that might be useful to detect forwarding loops. We added the operational consideration section to describe the difference between the SRH section and the SRH segment list section, where which one makes sense. And in the IANA consideration, we updated them to be in line with RFC 8126. The document itself does not introduce any new protocol. It's for documentation purposes only. However, because new IPFix registries are introduced, we specify the document as internet standard to be in line with other documents. Next slide, please. So data plane visibility is missing. Do you recognize the problem statements? We as author believe the document should progress quickly through IETF to avoid that private enterprise code points are being used at SRv6 deployments, and therefore we requested adoption at Ops AWG, and I'm looking forward to hear your comments and feedback. Questions?
One question, Ketin, go ahead, please.
Thanks for your work on this and also previously on the SRMPLS part, I should say. A quick feedback, not a question, on slide number 7. I think about the CSID container. I think I agree with your assessment that it doesn't add much value, at least in my opinion, to decompose it. Thanks.
Perfect, thanks.
Andrew, please go ahead.
Yeah, speaking as purely a working group participant, I just wanted to clarify, when you refer to CSID, are you also referring to GSID, same scenario, or do you see any differentiation there?
Since I'm not aware of GSID, I have to double check, but I will get back to you on the list.
Darren, please go ahead.
Yeah, just to build on what Ketan had said, I don't think there's any value in decomposing. In fact, I think it's better not to make any kind of guess as to what a behavior is of any of these SIDs. Just transport them and let the receiver determine what the behaviors are.
Mhm. Thanks.
Okay, there's no more questions in the queue. Can we move to the next presentation? Thank you. Joel, can you load the next presentation?
Trying to, but I'm having trouble finding it because I thought it was MPLS and SRv6, SRMPLS and SRv6 interworking, but I don't have a deck with that name on it.
Let's see here.
What's the deck name for this one?
The deck name is SRv6 and MPLS interworking only. That's what I sent.
It's there, Joel.
Uh,
Third one down on the list. If you look at the meeting materials.
Not on the meeting materials. Look on the shared deck. Let me go make sure it's actually shared properly because it may have gotten uploaded late. Sorry. There it is. That's the problem. There, it wasn't in the repository, so now it is, and I'll be able to share it. Sorry for the delay. The problem was this got loaded after they preloaded the stuff for us. So go ahead.
Thanks, John. Hi, everyone. I'm Swadesh Agarwal from Cisco. So, yeah. So this draft provides the SRv6 and MPLS interworking for end-to-end layer 3 and layer 2 services across a network. So this draft presents the interworking scenario into generalizes the interworking scenario into so that into a simpler topology as I'm showing in this slide. So if you see, green is showing a SRv6 domains, orange is showing MPLS domain, and the dashed oval is showing a box where the interworking functions are done. This is a border router between such domains, which provides the interworking function and supports both SRv6 and MPLS. So in this slide, we are trying to generalize the problem into a transport interworking and the service interworking. What transport interworking means is we have a layer 3 and layer 2 services, which are either SRv6 VPN or MPLS VPN. And the service interworking that we are trying to show in the bottom is a case where we have a SRv6 VPN working with an MPLS VPN to provide service connectivity, even though the service signaling is discontinuous. It's not of the same type. And can you go to the next slide? So this draft introduces new behaviors to provide that interworking functions that I showed in the previous slide on the border routers. So first function that we introduce is a first behavior is a DTM behavior. And what it does is when we receive a SRv6 packet where the destination matches the DTM behavior, we decapsulate the IPv6 header, and below that we are carrying a MPLS payload. So we do a lookup of the MPLS payload, and we send the traffic further based on the MPLS labels below the IPv6 header. Next slide, please. This is a new behavior, another new behavior. Again, this is executed on the as an interworking function on those border routers. And in this case, what we are doing is we receive when we receive an IPv6 packet which matches the DPM behavior. So it decapsulate the packet, and whatever is the associated MPLS stack with this behavior, that's pushed onto the packet and further forwarded based on the new stack of labels being pushed. Next slide, please. Yeah, so here we are trying to say that these are new encaps behavior for the MPLS stack, because when we receive traffic from the MPLS domain, we need to encap that into IPv6 header. So this is a new h.encaps.m behavior, which takes the MPLS stack as an input and adds the IPv6 header and the SRH uh, in, above it. Together, MPLS label stack and its payload becomes the payload of the new IPv6 packet, and the next header field is set to 137 because it's carrying an MPLS payload. Also, there's a reduced version of it. Next slide, please. Yeah, so this draft uses the idea of interconnecting binding sets. So binding set is bound to an SR policy as per the RFC 8402. So an SR MPLS label can be bound to an SRv6 policy. That's a binding set for an SRv6 policy, as well as an SRv6 set can be bounded to an SR MPLS policy. So once we do that, we can use these B sets in the segment list of an SR policy, which is an SR policy would be a consistent because we are using the binding set of a different type, and it represents the intermediate domain of a different data plane. So what I can do is in an MPLS, if the header is MPLS, I can create an MPLS binding set for an IPv6 SR policy and use that binding set to represent the intermediate data plane in my policy. And that way we can provide we can present the policy to the head end. Next slide, please. So now I will go into the how do we create these states on the interworking boxes or these functions. So we use in the transport interworking, as I mentioned earlier, we are trying to uh, reach the transport endpoint or the service endpoint. So what we do is, in this case, we use the well-known procedures of SRPC, where we provide a path using the SR policy, which satisfies a certain intent across the multiple domains. SRPC detects the data plane discontinuity because it is getting a BGP LS feed, and it can identify there's a network which is not of the data plane type of the head end, where the SR policy is to be programmed. Also, we use the BGP interdomain routing 3107 procedures, which to advertise the egress endpoints PE locators, or we can say service endpoints, which are PE locators in the SRv6 VPN, as well as IPv4 PE loopbacks for the MPLS LSP in the multi-domain network. And advantage of BGP interdomain routing is when you do next hop self on these uh, border routers between these domain, it provides the termination of the next hop as well as of the end cap. Next slide, please. So these are the few legends that I'm using in the slides. One is green means SRv6 capable node, orange means MPLS capable node, and the green and orange in the circle means it supports both MPLS as well as SRv6 capable node. Next slide, please. So here I'm showing how we can make an SRPC based solution for the interworking. So what happens is node 10 is a PE, which is advertising the VPN service prefixes, VPN prefix with the SRv6 service set, which I'm showing as a B10 as a locator of 10, followed by a DT4 function, which is a per verb lookup. And then it's advertised with a certain color red, which tells the intent. This is received by the node 1 through the service RRs, but node 1 is sitting multiple domain away, which is not a common IGP. So what node 1 does, it doesn't know how to reach the node 10. It will go to the SRPC with we're asking for a certain intent. That means it could be a low latency to reach the node 10. SRPC will compute the low latency path from node 1 to node 10. And in this case, I'm assuming it's node 2 in the domain 1, node 5 in the middle domain, which is MPLS, not the SRv6, and the node 8, which is again back to SRv6. So what it does is the SRPC sees there's an inconsistent data plane in middle, and it triggers the interworking procedures on the border box, in this case, which is 4 and 7. So it programs an SR MPLS policy on node 4, as you can see by the sequence number 3 from SRPC, and it is allocating, even though it's an SR MPLS policy, along the SLA path for node 5 to node 7, but it is bounding it to an SRv6 policy of a BM behavior. And that policy is programmed, and that binding SID is programmed on the head end node 1 by the SRPC, that is shown by the sequence number 4. And if you see the policy on the node 1, it has node 2 as the first segment. Then there's a binding SID of the BM behavior on the node 4, then the node 8 by a node 8 endpoint, and then the node 10 endpoint. So what happens is, now when the traffic, of course, it will visit the node 2 end function and update the IPv6 destination at the segment left. On the node 4, it will execute the BM behavior where it will put the MPLS, it will update the destination address to the next IPv6 address, which is the node 8, but it will also push the MPLS stack there. So once it pushes, it takes through the SLA path in the MPLS middle domain, and then at the node 7, of course, it will because of the PHP on node 5, it will when the packet reaches the node 7, it would be an IPv6 packet, which will take you to the next destination address, which is node 8, and finally it will be delivered to the node 10. So we can see how we can use this logic to provide the interworking in the SRPC case. Next slide, please. So this is exactly same.
Sorry to interrupt. You still have 5 slides to go on less than 2 minutes. So.
Sure. So I will quickly finish. I think the idea has come across. It should be fine. Thanks. Yeah. So this is exactly same idea, but here we are seeing the ingress domain is MPLS, and a middle SRv6 domain SR policy is allocated in MPLS binding SID, and that's what we put in the segments on the head end on the node 1, and that's the way we provide the interworking. Next slide, please. Yeah, so this one is a case of a BGP procedures, and we know in BGP we can always do the next hop self on the border node, in which way I'm showing node 7 and 4, and which can terminate the certain NCAP and then advertise the new one. So in this case, what we are trying to show is this is SRv6 VPN end-to-end. So we need a reachability to a locator of node 10 if the traffic is destined from the node 1 to node 10. So what happens is we can advertise the IPv6 locators in the right node through an MPLS domain in the middle, which is a 6PE solution. I can always advertise the IPv6 addresses with the IPv4 next hop and with the explicit null, and that way it provides the reachability of the locators to the left node through an MPLS network. It's an existing X6PE solution. Next slide, please. And similarly, to provide the over the MPLS over an SRv6 network, what we do is, in this case, it's the 1 and 10 are the legacy Ps, which is MPLS VPN. So we use the existing MPLS 3107 path here. So we have a 3107 labels on border nodes 4 and 7, which goes till node 1. It's an existing BGP-LU setup. Just that from 4 to 7, we tunnel into an IPv6 tunnel, which is of the SRv6, and the destination is to be of DTM behavior. So that way we provide the tunneling. Next slide, please. I think I can skip this one. We can go to the next slide. Yeah, summary is this document has been in the IETF from October 2018. The draft describes both the data plane and associated control plane procedures. For data plane, we have defined the new behaviors, DTM and DPM behaviors. And we also introduced a concept of internet connecting binding SIDs to traverse the heterogeneous data plane. For control plane, we provide both SRPC and BGP-based solutions. Next slide, please. Yeah, so I'm looking for the working group adoption for this document. Thank you.
Okay, we have 3 on the queue. Sally, I hope I pronounced that correctly. Please go ahead.
I am Sali from Juniper Networks. One question, basically regarding this SRv6 end behavior end.dpm. We have already have an exact similar SID end.dm defined as part of draft Bonica Spring SRv6 and DTM, which has been presented a few times in the Spring working group as well. I see the definition is exactly the same.
Sunny, this has been even in this draft for a long time. Earlier, we used to call it a decap variant of BM, but now we call it a DPM. So I'm not sure which one is the earliest, but yeah, we can work together to, if you feel it's the same, we can work together to come with a common name, if that's what.
Okay, thanks.
Dhruv?
Hi, Dhruv here. Swadesh, one question, maybe with my PC chair hat on. In your analysis for the SRPC solution, is there any gaps that you had found while describing the solution?
So
Gaps in the
Dhruv,
protocol extension?
yeah, Dhruv, so I have to work with the SRPC team, but if you see the BGP LS feed is available to the SRPC and it is available, it is aware of the topology. So it can easily figure out that it's an inconsistent data plane and can put a policy like a hierarchical ODN, a sub policy on the MPLS or SRPC's intermediate domain and pass it as a SID to the head end. So I don't see any gap, but of course I can work with you or somebody to see what is required if something is required.
Yes, Swadesh, I think in a single PC case, it is pretty clear that it's easy to do. What I'm worried about is multi-PC case where you have different PCs, maybe one PC is for SRv6 domain and another for SRMPLS. Doing that there would be little tricky. So that and might require some PCEP extensions as well. There is a working group draft in PC which talks about how to do stateful interdomain paths. So there might be some changes required there as well. So I think maybe we need to discuss this offline, how to progress this. Thanks.
Sure, Dhruv. Probably I will set up something with you and see what we can do, what is required. Sure.
Okay, last question. Robin, please go ahead.
Okay, Robin Huawei. My comments for this draft is that in fact this the interworking between the SRv6 domain and the MPLS domain, there's the complex the data plane. Because we know the SR advantage of SRv6 is to traverse the domain based on the IPv6 reachability. So I would like to encourage the operators to think about the requirement and also let's say if can take this the simple way or we need to define the complex the forwarding plane for the interworking. Yeah, that's I wish that the operators can have more feedback on this one. Okay.
Thanks, Rob.
Enter, please go ahead.
Jagan Babu, we're tight on time. Please start. Are you muted?
I couldn't hear you. Okay. Hello, everyone. My name is Jagan Babu Rajamonikam. I'm going to present the MPLS extension header encoding that are defined in our draft on behalf of all our co-authors. By the way, this draft has been presented in yesterday's PALS working group. Can you please move the next slide? Next slide, please. Yeah, so this slides talk about all the abbreviations which were used in the presentation and the draft as well. I will leave it to the user to look at it. Okay, so this is the agenda we're going to talk about in the presentation. Next slide, please. Okay, so there are many new applications are coming up with new requirements to carry an additional information in the MPLS packet to influence the MPLS forwarding or for the OEM purposes. So this requires an MPLS packet to carry more SPLs or ESPL per application, and this will increase the MPLS stack drastically. To solve this problem, we need a generic framework to build the MPLS extension header format that would carry multiple loading instructions in the MPLS stack or after the bottom of the label stack. The main objective of this draft or the MPLS packet should be able to carry two types of in-stack forwarding instruction. One, the flag-based instruction forwarding instruction that does not need any auxiliary data. And next, forwarding instruction that needs an auxiliary data. The MPLS packet to carry additional data after the bottom of the MPLS stack. And the third one is any combination of this in-stack and MPLS bottom of the stack forwarding instruction could coexist in the same MPLS packet. And the fourth one is the new solution which we're bringing up should be always backward compatibility. Next slide, please. Before diving into the solution, I want to let you know that we have done extensive hardware analysis to come up with the implementable, ASIC-friendly, and futuristic solution. So the MPLS extension header mainly consists of two parts. MPLS extension header indicator. So this indicates the presence of the MPLS extension header in the packet. And the second one is MPLS extension header format, the format in which the MPLS extension could be carried in the MPLS packet. Next slide, please. Let us see the different options of MPLS extension header indicator. Option one is to extend the existing ELI, EL by repurposing the ELs, TC, and TTL fields to indicate the presence of the MPLS extension header. Option two is to assign a new special purpose label to indicate the presence of the MPLS extension header. Option three is to use a user configure label to indicate the presence of the MPLS extension header. Each option has its own advantage and disadvantage. We could choose the options based on our discussion on the IETF working group. So here the fields, when you see the fields here, the first field is the in-stack data length. This is a 3-bit field, which is used to indicate the total length of the in-stack extension header in the order of 4 bytes. Some of the parser would require the length of the total length of the in-stack MPLS extension for the EC parsing purposes. Next is the bit field, like the IPI field. So this is actually in-stack MPLS extension header presence indicator. This is a bit field, indicates the presence of the in-stack extension header. And the next one is the BPI field. So this is the bottom of the stack MPLS extension header presence indicator. A bit field indicates the presence of the bottom of the stack extension header. So last field is the HPI. This is a hop by hop bottom of stack MPLS extension header indicator. A bit field indicates the presence of bottom of stack MPLS extension indicator that needs to be processed hop by hop. Next slide, please. This is the in-stack extension header and its data encoding format. So as I told you before, this has two parts. One is the in-stack MPLS extension indicator. So here actually the 2-bit, the IPI bit is used to indicate the presence of in-stack MPLS extension header. And the IL, that is the in-stack data length, is going to indicate the total length of the in-stack MPLS extension header length in the order of 4 bytes. So also like we could carry multiple such instructions in the same indicator. So next one is the in-stack MPLS extension format. This contains opcode, the in-stack forwarding instruction opcode. This is of 8-bit opcode that defines the forwarding instruction that needs to be executed when it receives the packet. And next is the in-stack data. This is an auxiliary data which requires to be executed, which requires to execute the forwarding instruction. And the D bit, what we define here, is a data stacking bit. In the case of instack forwarding instruction requires more than 20 bits of ancillary data, then this bit is used to extend and carry more bits of ancillary data. If this bit is set, then this will be the end of the ancillary data for that specific forwarding instruction. The, the last one is the E bit. So this is the end-to-end bit. This indicates whether the forwarding instruction has to be processed hop by hop. Let's go to the instack forwarding instruction opcode assignments. The value here actually we have opcodes will be assigned using the IANA registry. So the value 1 we have reserved it for to carry the flag-based forwarding instruction. In some cases, the application does not need any forwarding instruction does not need any ancillary data. So this opcode will be used to carry the flag-based opcodes. The value 2 is optionally used to identify the byte offset of boss data location. And the value 3 to 254 must be assigned by IANA. And the last value 255 is used to extend the opcode range beyond 255. Next slide, please. So this is the bottom of the stack header encoding format. So as an indicator, so we have 2 bits to indicate, 1 bit is to indicate the presence of boss MPLS extension header. So this is going to indicate the presence of boss MPLS extension header. And another bit is the hop by hop boss extension header. This field is used to indicate the presence of boss extension header that requires hop by hop processing. The second part is the boss data format. The first label is 0010. So this is to avoid aliasing with IPv4, v6, and v6 packets. Next label is reserved, and the next octet is the opcode instruction. This value will be assigned by IANA. The next octet indicates the length of the boss ancillary data in the order of bytes. And the next octet is used to indicate the boss extension header field. Currently, you have two flags assigned. One is the next header presence. This indicates the another boss MPLS extension header following, and the hop by hop bit indicates the requirement of processing the specific header hop by hop. Next slide, please. I'm not going to describe the next slide. This is the example actually. This is the example of how we can carry the data. These are the examples. Next slide, please. So this is the example. This is now like option 1 and option 2 comparison, which we want to talk about for the IETF users to discuss. Next slide, please. Thank you. Welcome review comments and feedbacks, especially on the MAI label options. And we requesting MPLS working group adoption currently. Thank you.
Okay, thanks. I actually have a question. Has this been discussed in the MPLS design team? I thought a lot of this work was going on there.
No,
also, I actually sent an email to the authors of this document several weeks ago and didn't get a response. There are several documents that already cover this, albeit with different format, and I'm wondering if those have been looked at in terms of making sure we don't have multiple documents trying to solve the same problem. Thanks.
Yes, Jim. Actually, yes, we know that. Like this doc, in the appendix, actually, we have given there are some documents available currently. So in the appendix, we have given the difference between their approach and our approach to say how it is parser friendly.
Okay. Okay.
I don't have time to discuss on this meeting, so.
Yep. Okay, Chong Li.
So I have a very simple question that what is the motivation? Do we need to work on this? Because it looks for me that we are reinvent something like the things in IPv6, but it would take a long journey to get that. When we get there, we have already deployed IPv6 everywhere. So I don't know. It seems like we're making Amperes very complicated. Is it clear? Is it right?
Actually, like today, like when you see these applications, right? A lot of applications are coming up with different requirements, which needs an additional SPL or ESPL. So that's going to increase the label stack. That's where like the design team has been designed to tackle this problem one shot. So that's why we are trying to do that.
Yeah, I get it. Like we have some issues in Amperes, but uh, where is the value? I don't get it because what we want to get is all about IPv6 capability. So why not just go there?
Yeah, let's take that discussion to the mailing list because we are short on time and there's a few people on the queue.
Yeah,
So,
thank you.
yep, Rakesh.
So two comments, Cheng. A good comment. Yeah, we hope to see the SRv6 deployed everywhere very soon as well. But meantime, MPLS network, we do have an IOM draft for MPLS in MPLS working group. And IOM is one application that's very appealing to the operators for MPLS. And the second comment I have is that, Jim, we have received your email. We are looking at the drafts that mentioned, and we will get back to you soon. Thank you.
Great, thanks, Rakesh. Greg?
Thank you, Jim, for reference to MPLS Open Design Team. It's a joint effort of MPLS, PALS, and that networking group. I think that Spring, because of SRMPL, MPLS, everybody, all experts are invited definitely to the open weekly design team discussions where we discuss other proposals, and use cases are documented in the draft as well separately. So the motivation being discussed as well as the requirements for the solution. So there is a work that's been discussed and reported on yesterday in the meeting, and so I appreciate their presentation, but I think that there are a lot of more discussions that needs to be done before consideration of working group adoption. Thank you.
Thanks, Greg. Lastly, Jeff, please go ahead. You're the first one in the room.
Jeff Tensura. So keeping aside whether it's metadata should be in data control plane, IPv6 over SRMPLS is deployed at huge scale. It is supported by most vendors, and ignoring it is just wrong. It's a good technology, it's working, it's deployed. So please just keep in mind that Vault is not about SRv6 necessarily. IPv6 over SRMPLS is currently working technology. So just keep it in mind.
Yep.
Can you hear me?
Yes, we can. Please go ahead.
Oh, hi, this is Li Hao from H3C, and I present this draft on behalf of the authors. This draft is about SBFD in SL6 network. Next slide, please. BFD and SBFD could be used to monitor passes between nodes. SBFD is suitable for large-scale network and supporting verification on reflector. BFD and SBFD could be used to monitor SL6 policy, essentially associated with a segment list to detect the continuity of segment list. Next slide. One uses SBFD to monitor SL6 policy. The control packet is forwarded to the reflector according to its associated segment list, and the response packet is usually forwarded to the initiator through IP routing. So the forward and reverse passes of the package are likely inconsistent as shown in the figure. The failure on pass DEA will cause a false positive issue. A consistency of forward and reverse pass should be guaranteed. In order to meet this requirement, and SBFD could be widely deployed in SRv6 network, this draft describes how SBFD to achieve the bidirectional path consistency of package when monitoring SRv6 policy. Next slide, please. Next slide. Okay. The method is based on the path segment. SRv6 path segment is defined to identify a SRv6 path, such as candidate path or segment list. SRv6 path segments can be used to correlate to all the unidirectional SRv6 passes at both end node. Under the draft of IETF SR policy, path segment proposes an extension to BGP SR policy to distribute SR policies with carrying path segment and bidirectional path information. Through this extension, when distributing SR6 policy to the head end, reverse path information and path segment of segment list could be carried together. In this way, node A and D in the instance have two path segments which are associated with bidirectional paths. Next slide. So the head-end nodes in both directions need to create a table to map path segment and reverse path segment to local segment list. Through this mapping table, the head-end node has the ability to get the segment list by path segment or reverse path segment. Next slide. The procedure for the SBFT module example in this slide is node A as initiator, which has a SBFT session associated with segment list 1. First, the SH is encapsulated with segment list 1 to the control packet. If it has path segment encapsulating the path segment in SH and set P flag, then the control packet will reach reflector with the path segment of forward path. By the way, the draft use SBFT echoes example rather than the control packet, and we will fix it. Next slide. For reflector node D, SBFT module needs to detect flag of SH. If a P flag is set, extract the path segment of forward path from SH, then get a segment list for response control packet by the forward path segment, and the resulting segment list will be used to encapsulate response control packet. If P flag is not set, response packet will be forwarded by IPv6 routing. So use the path segment and forward and reverse path of SBFT are guaranteed to be consistent. Next slide. Okay, that's all. Question or comments welcome.
Okay, thank you. There's nothing on the queue. So, Joel, can we get the next presentation up?
Trouble finding the deck again. Just a moment. End to end. There it is.
Robin, up to you. You have 10 minutes sharp.
Okay. Okay. This is Zhengbin. I will present the SR for the IETF end-to-end network, end-to-end IETF network slicing on behalf of the co-authors. Okay, here's some of this background introduction. First, we are familiar with the network slicing, as the network slicing can be used to meet connectivity and performance requirement of different service or customer in a shared network. And this is the draft IETF TIS IETF network slicing describe the concept and the general framework of IETF network slice. That is, IETF network slice can be realized by mapping one or a group of connectivity construct to an NRP. NRP means network resource partition. In fact, before that one, there's the one draft about the framework of the enhanced VPN. So in here, there's the VPN concept is proposed to mean the underlay network slice construct, but is not only confined to the network slice. So NRP is an instantiation of VPN in the scenario of network slicing. Okay, and third one, this end-to-end IETF network slice may span multiple network domain. So this means the network slice will traverse multiple network domain, and in each domain, IETF network slice traffic needs to be mapped to a local network resource partition. So this document describes the segment routing extension to support the end-to-end IETF network slice. Okay, next page. Okay, so here this is just the glass of the IETF network slice framework and the VPN plus realization. So here we can see there the general concept and framework, and also the VPN plus framework and the end-to-end 5G E2E network slice. And this after this the framework in the past years, we defined the SR-based network slice realization. The most important to use the resource-aware segment for the network slicing and indicate the resource partition. And then there later the scalability is a challenge. So the scalable IETF network slice realization solution has been proposed. The major concept for improving the scalability to decoupling the topology and the resource, so that the network resource partition ID can be carried in the data plane to indicate the specific resource for the specific network slice instance. So according to this method to decoupling the network topology and the resource to improve the scalability. That is 1 month ago also that the IPv6 encapsulation for the network resource partition ID in the data plane. The draft has been adopted by the working group in 6 months. So now that we talk about this end-to-end IETF network slice realization. So this means how to implement the inter-domain IETF network slicing. So this is the draft. Okay, next page. Okay, so here the concept is simple. That's to use this binding segment. But here this introduce a special binding segment called the NRP by the binding segment. This segment is a special BSID used by the domain nodes to steer traffic into a local network resource partition. So, and this the network resource partition BSID can be instantiated with SRv6 or SRMPR's data plane. So here there's a simple the illustration. So we can see that the ingress of this the inter-domain SR path. There's this the 3 binding seed for the network resource partition, and so that's for each edge nodes for the each domain will based on the network NRP binding seed to steer the traffic into a local NRP. So this is just the SR for the end-to-end IETF network slicing. Okay, next page. Okay, in fact, before this version, so that's we propose that's four types as NRP binding segments. But later, this version of the draft, we divided the NRP binding segment into 2 types. That means NRP TE binding seed, NRP BE binding side. The NRP BE binding side is to steer the traffic to an SR policy associated with the local NRP. NRP BE binding seed is not to steer traffic to an SR policy. It's just to steer traffic to follow the shortest path within a local domain NRP. And for the NRP TE binding side, there's the 2 variant. The first variant is based on the SR seed network slicing realization. So that's use this binding seed to specify the mapping of the traffic to a SR policy, which consists of list of resource aware segment associated with the local NRP. Okay, that means the binding seed to indicate SR policy, which is composed of the resource aware segments. The second variant is to use one type of NRP binding set to specify the mapping of traffic to a SR policy, which is bound to a local NRP ID. So this means this indicate SR policy. At the same time, there's NRP ID is bound to this SR policy. Okay. And also for the NRP, sorry, NRP BE binding side, there's the 2 variant. The first variant, that's this binding side, is directly to indicate a NRP, local NRP at the edge node. So that's there's one binding side, there's one local NRP, then there's a NRP BE binding side. So that's the first variant. But we also have the second variant. So that means only there's a binding seed to indicate the there's the local NRP to be bound at the edge node of the domain, but the NRP will be specified in the ingress of the SR path. That means the SR the NRP is the encapsulation of the ingress of the SR path, SR policy. Okay, so here this is the SRv6 for the NRP binding side. So here we have this the SRv6 the NRP TE binding side. So that's the RC 8986, the end B6 in caps. This behavior can be reused, and this document defined the end dot B6 NRP dot in caps. This another behavior for the second variant, and for the BE binding side, we also have the 2 variant and also the 2 end behavior to be defined. Okay, next page. Okay, so this similarly, so this for SRMPS, there's also this the different instantiation for this the NRP binding side. Okay, last page. And this is a summary of the updates. So the first align the terminology with the IETF network slice and the VPN plus draft. That means we adopted the NRP as the terminology to replace the VTN. Second, we define the two types of NRP binding segment for the SRTE and the BE, and also this editorial change. Okay, that's the page. Okay, we in fact we updated the draft yesterday, so that's the comments and feedback are welcome, and we will go on to refine this draft accordingly. Okay.
Thanks, Robin. Linda?
Thank you, Robin, for the comprehensive illustration of all the drafts you have for the VPN Plus. I just have one question. Like for 5G, we really need something to have different paths based on the source address. So is any of those drafts, I didn't get a chance to read all of them, any of the drafts describe that?
In fact, this draft is regarding is related to the IETF network slicing. That means the transport network. But this is not for the 5G end-to-end network slice realization. This is
Well, even for transport, for example, the traffic come to the UPF, right? So based on the UE, for example, in the compute aware network involved, when different UE, like maybe hand over to a different cell tower, anchor to a different UPF, he would like to use a different slice than the other UEs, which were there before. So it would be nice to be able to, like, based on the source address, and then allocate to different slicing. I'm just wondering if there's any draft describing that.
Okay. In fact, this draft is not for this purpose. In fact, there's the two drafts about the 5G end-to-end network slicing. I think this is in fact, the 5G traffic will not directly enter into the IETF underlay network slice because the traffic from the UPF will first interworking with the VPN of the transport networking. So here they can use some of this the VLAN for the interworking, so that to access to the VPN, so that the VPN can go on to mapping to the underlay NRP. So this is the case. And also that's one draft in the TIS working group. We have the one draft that is we can take some of this the end-to-end 5G network slicing identification. Based on this identification, we can use this one can directly map to the IETF network slicing, but that is still in the early stage. So that's all. Okay.
Thank you.
Reza.
This is Reza Rokui from Siena. Just answering Linda's question, you mentioned about how this one relates to 5G. There are a group of RFC drafts, or the draft at the TIS that I'm encouraging you to take a look. I can send you a handful of those drafts. But in summary, the whole idea of the creation of IETF network slice is different from the usage of that during the signaling, because when you refer to UE, that is the signaling part. That is the orthogonal action which happens. You are creating IETF network slice, which means that you are connecting logically subset of your network to the 5G RAN and 5G core mobile. And after that, you are going to use it. So just for clarity, UE and anything related to signaling is orthogonal to the IETF network slice. But I will send you some of the draft, and if you want, we can talk offline. Thank you.
Thank you.
Okay, thanks. Ahmed, please go ahead. Ahmed, we can't hear you.
Hello, everyone. Can you hear me now?
Yes, we can. Go ahead, please.
Okay, thank you. Thank you, James. So hello, everyone. This is Ahmed, and I'm going to be presenting the path tracing in SRv6 network draft on behalf of the co-authors. Next slide, please. So this is the agenda for the presentation of today. Next slide, please. Next slide, please. So path tracing basically is a solution that would allow operator to deterministically detect the actual path of the packet, or in other words, to discover the available ECMP passes in a given network and their characteristics. So what path tracing provides is a record of the packet path as a sequence of interface IDs. And on top of that, it provides a timestamp for end-to-end delay and also pair hop delay. And in addition, the load on each egress interface along the packet delivery path. This has been designed for line rate hardware implementation in the baseline, as it requires really a minimum header size, and you can see in here in one example with just 36 bytes hop by hop option, we can actually record the information of the path for 14 hops. And also has been designed to be hardware friendly, so it requires the same editing across all of the nodes in the network, regardless of the position of the node. Next slide, please. So basically, path tracing is applicable to both SRv6 and SR-MPLS. In this document, we define the path tracing specification for the SRv6 data plane. There will be another document defining the SR-MPLS data plane specification. Next slide, please. Here are some of the terminologies that we will use during the presentation. So especially what we call the midpoint compressed data. And this is basically the information that every transit router along the packet path add into the packet. And it is actually just 3 bytes of information, which is a key compression to support path tracing at line rate, in addition to some of the headers that we use in the packet. So we define a new hop by hop option, what we call it HPHPT, which will be used to collect the data from each node along the path. And we define also another SRH path tracing TLV, which will be used to collect the path tracing information both from sink and source nodes. These 2 headers will be defined in this document. Next slide, please. So one of the main key elements of path tracing to allow supporting that in hardware at line rate is basically to collect a little amount or minimum amount of bytes from each node in the path. So what we collect in path tracing, we call midpoint compressed data. And it's 3 bytes of data, as you can see. Here's the format on the right of the slide. And these 3 bytes of the data consists of, first, the outgoing interface ID, which can be an 8-bit or a 12-bit interface ID. And it is associated with the egress physical port of the router. The second piece of information of this midpoint compressed data is basically the outgoing interface load, which is a 4 bits of data that represents the egress interface load. And finally, we have an 8 bits of timestamp, what we call it the truncated timestamp. And basically, this is an 8-bit timestamp encoding the time at which the packet leaves the router. This timestamp actually has a different significance based on the link type. And this is what we call the TTS template or the time template. And this is something to be configured by the operator. Next slide, please. So in the path tracing data model, we have different roles, which include the path tracing source node, the path tracing midpoint, and the path tracing sync node, as well as a regional collector. This is what we will be covering in the next couple of slides. Next slide, please. So in path tracing, the first node that gets triggered here, or the first role in the path tracing data model, is the source node. This source node basically generate a probe packet, or the node that originates the probe packet. The format of the probe packet you can see here on the right side of the slide. We have an IPv6 header and hop-by-hop header with a path tracing option. Then we have a segment routing header with a segment routing path tracing TLB. The source node, after it creates this packet, it decides in which interface the packet is going to be sent using the normal forwarding, and it records its information in the packet just before the packet leaves the router. Next slide, please. The second role here is the midpoint. This midpoint receives the probe packet that was generated by the source, perform an IPv6 forwarding or an SR endpoint behavior, and before also forwarding the packet out from the node, it records its MCD data in the hop-by-hop path tracing option. Next slide, please. At the sync node, we support a new SRv6 behavior. We call it end.b6.tef, which refers to a binding seed with timestamp encapsulation and forward behavior. This SRv6 behavior encapsulates the received probe packet with an outer IPv6 header, SRH, and path tracing TLB. As you can see here, the format of the packet after being forwarded by the sync node is on the right of the slide. The sync node will record its path tracing information in the segment routing header TLB and will forward this packet to a regional collector. Next slide, please. The role of this collector is basically to receive the probe packet, extract the path tracing information, and save them into a time series database. The path tracing information in the time series database will be used by operators, basically to perform all of the different analytics. Next slide. So in path tracing, actually, we define two new headers. The first one is a hop-by-hop path tracing option. The format of this option as shown here. So we have an MCD stack that will be a pre-allocated space for the midpoint to record their data. The hop-by-hop option is to be assigned by IANA, and it should have the three higher bits set to 001, so 00 for node that does not support path tracing to skip the packet, and 1 for the node that support path tracing to record its data. Next slide, please. We also define a new path tracing TLV. This is the format of the TLV. It will get a type assigned by IANA, and it will be used to record the source and sync data from the path tracing information from the source and sync node. Next slide, please. Regarding the security of model for consideration for path tracing. So in path tracing, we leverage the security consideration defined for the segment routing domain as defined in RFC 8754. Also in path tracing, we require that the hop-by-hop option must be processed in the fast data path. So therefore, it cannot be used as an attack vector against the CPU. Next slide, please. So we have some experimental and interoperable implementation for path tracing, and this includes some hardware from different vendors like Cisco, Broadcom, and Marvell. And we have also some experimental open source implementation, including FDIO, VPP, Linux, and Wireshark. Next slide, please. So we welcome the review and the comments from the working group. In particular, we would like to ask other vendors to review the data plane model for path tracing and give their feedback if we need any more optimization or the data plane is good to be supported at line rate by other operators, by other vendors. Thank you.
Thanks, Ahmed. Greg, please go ahead.
Just in few words. So this is a redundant proposal. Everything that you are achieving can be already achieved using IAM, and even more, because IAM has advantage of collecting telemetry information out of band without impacting the data flow by incorporating telemetry information in a trigger packet. So that can be achieved using direct export option of trace or hybrid two-step option. And I'm happy to discuss it on the mailing list more, but this proposal is redundant. Thank you.
I believe the two proposals solve the problem from different angles as we discussed on the mailing list, but I will be happy to have more discussion on the mailing list.
Chong-Li, please go ahead.
So I could like to know the relationship between this proposal and ROM. And by the way, I'm really curious about the timestamp format. I think it would not be so accurate. Yeah. So oh, okay. So 2 years ago we have a similar solution called Light IOM. So I can prepare the link for the reference. Yep.
Okay. So again, for path tracing versus IOM, I believe again that this solves two different problems. Especially path tracing has been optimized for line rate hardware implementation, but we can discuss more on the mailing list on that. Thank you.
Thank you.
How are you? Please go ahead.
Yes, I just want to say that I share the same opinion as Greg, and we do need to make a fair comparison with IOM, and if IOM can achieve the same goal, it seems unnecessary to have another solution. Thank you.
Okay, last Pablo, please go ahead.
So just one comment on the comparison with IAM. I believe that the issue that we are facing with IAM is that the data plane design, when we do not want to do direct export, it becomes quite complex to support in any device. Particularly not only because the data feeds are large, but also because the amount of editing commands that you require to implement it in the actual hardware. And so basically, if you want to do ECMP monitoring and troubleshooting, collecting the data from the data path itself, I believe there is no way to solve that with IAM. But anyway, we are happy to discuss more on the mailing list. Thank you.
Sally, please go ahead.
Hello, am I audible?
We hear you.
Okay, thanks. So I am Salih from Juniper Networks. I am today presenting the draft SRv6 in the domain mapping sheets on behalf of my co-authors. Can you go to next slide, please? Yeah, so we had presented the initial version on the IETF 112, and these are the updates from the last version. We have two new co-authors. We thanks their contribution. And we have enhanced some SID behaviors to cater to cases like OAM. And we also added a section on interworking procedures by taking examples for the use cases we defined in the draft. Yeah. So basically, this draft had mentioned 3 new SRv6 endpoint behaviors named n.replace, n.replace b6, and n.db6. So these behaviors actually helps to build paths across different SRv6 domain one operator has. The document mentioned 2 use cases. One where the option C multiple ASs connecting, where the borders are connected via eBGP. And then there is a second use case where we have option B style interworking. So the n.replace and n.replace b6 are for the first use case for the option C style connectivity. So what the changes from the last revision is we have added a section. Normally this n.replace cannot be the last segment in the SR policy. So we extended this when the segment list left equal to 0. We have updated similar to the other SIDs mentioned in the network programming RFC 8986. So the remaining definitions remains the same. Can you go to the next slide, please? Yeah, so here also the this n dot replace b6 it also cannot be the last segment in the SRH. So similar to the previous SID, we have enhanced segment left equal to when the segment left equal to 0. We talk about how to handle similar to other SIDs, and then we also have added few notes on how to fill the fields of the new encapsulation headers, and also talks about an optimization for best effort and FlexAlgo scenarios when FlexAlgo is used or best effort path is used in the domain. Can you go to the next slide, please? Yeah, so this for the this n.db6 is used for the second use case for the service interworking. So as per the definition, it must be the last segment in the SRH. So different from the other 2, we have changed when the clarity for normal processing. So when the upper header, we clearly defined IPv4, IPv6, and Ethernet. And then if it is not belongs to that, how to process similar to the other embedded behaviors. So here also clarity has been provided on a few fields on the new NCAP header. Next slide, please. Yeah, so a new section we have added on the interworking procedures. It describes the procedure by taking examples. It talks about both control plane and data plane flows. So here, this is all the first use case option C interworking example. So there are 3 different SRv6 domains connected via eBGP, and within the domain there is IBGP connectivity. And there could be, in this example, we have taken 3 SRT different paths. Each AS has a different SRT path for the transport. So these 2 SIDs, this replace B6 and replace SID. So the common logic is for a route, if the next hop is 1 hop away, then while advertising we use n.replace SID. For a route, if the next hop is multi-hop away, then while advertising we use n.replace B6 SID. And for a single hop neighbor scenario, there is no NCAP required, as it is just a replace or a swap. Yeah, so the more details on control plane and data plane that is explained more in the draft. Yeah, this is the next use case. So where there is option B connectivity, the 4 is acting as the ABR or RR, where the service interworking, the stitching DB6 is advertised from the node 4. So for all prefixes having the same service SID, same DB6 SID will be reused. But if a different service SID, different DB6 will be used. So this ensures that if the egress allocates per C SID, the translation at the node 4 also ensures per C behavior. Yeah, so the DB6 SID is advertised it is allocated at the node 4. So this is for the option B. Here also the draft takes how each control plane and data plane messages flows through the network. Yeah, next slide, please. Yeah. So yeah, we request working group review and comments. Also, we are requesting working group for adoption as the next steps. Thanks.
Okay, thanks. Ketan?
Talavlikar. Thanks, Sally, for the presentation. I had a clarification question on slide number 6. If you could go there. I wanted to, if you could go back to the slide, Joel, if it's possible. The question was, why do we need a replace in that scenario? One more, the option C. Yeah, thank you, Joel. On this slide, why do we need the replace behavior in the first place? I think you mentioned something about SR policies, but I didn't quite get that. I mean, in option C, why couldn't one just directly reach 16?
Yeah, so why we are taking two different seats, right? So that, as we mentioned, if it is if the AS has only best effort or flex algo, that optimization we can do. We don't need an additional NCAP. But if it has an SRT policy, then we need, because we need to first reach from one border to other border. So we have to replace first, so that the other border understand what to be processed next. So that's why the first change in destination we have to do. But then there is an additional NCAP required for that the upcoming domain, right? Because that SRT path that has to be on a new NCAP. So that is that's why that for SRT cases we need that extra NCAP.
Okay, so if I understood you correctly, there is a underlay a BGP that you have, and the replace is used or needed by that underlay BGP.
Correct.
And this is probably in the car or city
Correct, you're
context, right?
right.
Okay,
You're right.
Thanks, Sally. Thank you. It was not very clear. Thanks for clarifying.
Thanks, Ketan.
Hello, everyone. I'm going to talk. This is Hao Song from FutureWay. I'd like to talk about this SRv6 in situ active measurement on behalf of other co-authors. Next slide, please. Yeah, first the update from the initial version. Now we reposition this as a generic framework for SR6 active measurement, and we can support other active OEM protocols in addition to IOM under the same framework. Also, we have a new co-author, John Mishra. Next slide. The motivation for this work is that we believe the SRv6 need active measurement method, and also active measurement method is also very suitable for SRv6. Because SRv6 has this traffic steering property. It can support arbitrary paths specified by SRH, and also we can start the probe from any SR node and terminate and another or even the same SR node. So which means it's very flexible to apply the active measurement. And also the forwarding is totally determined by the SRH. That's why using this, we can also physically reflect the data plane user traffic experience. It has many possible potential solution applications. First one is to achieve the network-wide visibility. We can use smart algorithms to actually build the different SR paths to cover the entire network for the network-wide health monitoring and troubleshooting. And also, we can easily achieve the alternative path probing for protection, traffic engineering, or multi-path load balancing. Using this, we can also easily to achieve the symmetric or asymmetric round trip measurement. So we just define the path and make the packet return back to the south, so we can get the measurement. So this framework, the general to use a UDP payload to encapsulate the OAM protocol header and the data. We can use a different UDP destination port number to differentiate the different protocols. Sorry. And also, we propose to use a T flag in the SRH flag field to indicate this as an active probe packet. This is important because without such a flag, the packet may be mistakenly considered as a normal user packet by the SR nodes and be ignored. So in this draft, we mainly focus on IOAM as a chief use case. And also, there's another draft already being adopted by the working group. It's talking about how to support SDAM as a use case. But here we also suggest to augment that draft with this T flag to indicate the active measurement packet. And there are also other possible use cases, for example, to support IOM direct export and alternate marking schemes, all can be supported under the same framework. So this slide shows the format of the SRv6 active measurement with IOAM. After the SRH header is followed by a UDP header. We can use a destination port to indicate the payload following it is IOAM. Then we can apply the standard IOM header after as a UDP payload. And there are some benefits for this scheme is because here everything is already being standard. There's no need to have a new standard proposal. And also IOM can support flexible and extensible data extension. And since we encapsulate the entire IOM in the UDP payload, there's essentially there's no limit on segment hops. We can support very long paths to collect all the data. Next slide. Oh, I can't read it. Oh, why does it look like this? Okay, there's applications. I already talked about this, but I will just emphasize that it's an easy way to support. It can be considered another easy way to support IOM for SRv6 without the drawbacks of encapsulation or the overhead concerns. And also, we just use this as an active method to measure the alternative paths, round trip, or cover the entire network. Here I list a reference, another draft actually talk about how we can use smart algorithms to actually calculate the minimum number of passes to cover the entire network, and take advantage of the traffic steering capability of SRv6 to gain the full network visibility. Next slide. Okay, so next step, we'd like to request for working group adoption, and of course we welcome all the comments and the reviews. And in the next revision, we also consider to include other cases. Thank you.
Thanks, Hao-Yu. Greg, please go ahead.
Presentation. Clarification question. So how this proposal related to IPPM working group document that defines IAM encapsulation in IPv6?
Okay, I think this one is a focus on the active measurement, but that one is I think is for the original use of IOM is considered as a hybrid method and mean to encapsulate IOM in user traffic. But here we just use it as a dedicated probe. only for the active. Yeah.
My understanding that IAM can be applied to active IP OEM packets, so to achieve everything that you are proposing. So I don't understand why you're really emphasizing active OEM. Active IP OEM in SRv6 uses regular IP OEM like ICMP or IP encapsulated stamp or BFD. So yes, explicit routing allows us to engineer the path that test packets takes. So it's equally applicable to all known OEM in IP. So applying IAM to that is not a rocket science.
Yes, a unique feature of the IOM, you also understand, is that we can actually collect all the data along the path, and while most other OEM techniques is only work in the edge-to-edge or end-to-end fashion. So I think IOM can bring the unique, benefits to this active measurement area.
Yeah, but it appears that you are proposing a solution to problem that already solved.
Yeah, as I said, that solution is proposed to encapsulate the IOM in maybe in other extension headers, and it's intended to be used for user traffic, and also, in my opinion, it's bringing some issues about encapsulating IOM in the extension header because of its huge overhead. And also there's some consideration about how to actually use as our IPv6 extension header. So I think here we just avoid all those issues, and it can be deployed immediately.
I would propose, if you're not happy with the IPPM working group draft, why not work with IPPM working group rather than proposing alternative solutions? So driving IETF to standardize two ways to encapsulate IAM in IPv6. So to have IPv6 general and special SRv6. That seems not a good approach.
Yeah, you already seen there's already another working group draft talking about supporting stamp under the same framework. So we already have this. Why we let's just use it?
My understanding
that's
that
an easy step to go. Yeah.
No, my understanding that stamp draft in Spring working group is informational because it doesn't define anything. So, but let's take it to the mailing list. Thank you.
Okay, thanks. Wei Cheng, are you there? You're up next.
Yeah. So thank you, Chuck. Could you hear me?
Yes, we can.
Okay. This is Wei Cheng from Channel Mobile, and so this is a new draft. It gives some good practice to use the SRv6 policy. So let's see the requirements and the proposal. Here, let's see the application scenarios. And first, some enterprise customer have different kinds of services with different queues. They often hope to forward those different services with different SR policies. The policies for one customer, we hope to form an SR policy group. So here's a SR policy group means a special SR policy, which contains a group of constituted SR policies. It can be identified by color and endpoint on the header end. It's the same with SR policy. So let's see the criteria. The endpoints of the constituent SR policy and its group should be identical. And the color of each constituent SR policy and its SR policy group should be different. So what's the value of the SR policy group? I think firstly, we can configure the policy based on the customer with different SLA services. It can improve the efficiency of the network operation. And it can also bring some fallback solution or something like that. Let's go to next slide. So how to use SR policy group? I think firstly we should story the traffic into SR policy group. We can have two kind of ways. First is per flow storing. If you want to do that, you can take two steps. First step, you should steering the flow to the SR policy group. And the step two, select the constituent SR policy of the group. Similar for the policy-based steering. And the SR policy group can be configured manually or distributed by the controller, or you can create through ODN automatically. Next page. So here is use case, how we use the policy group. In the figure, we have three policies. The policy A is a low latency path for the VIP customer. And the policy B is the normal traffic for the VIP customer. And the policy C is the normal traffic for the non-VIP customers. And we use the DSAP to map to the color. So let's see how it works. When the PE1 receives the traffic, which maybe is a SR policy group from PE1 to PE2. Firstly, it matches the SR policy group according to the next hop and the color of the road. And then finds the constituent SR policy in the corresponding group according to the DSCP. And the voice traffic of the VIP customers will be forwarded to the low latency constitute SR policy A. And the other traffic of the VIP customers will be forwarded to the policy B. And the non-VIP customers traffic will be carried by the policy C. So it will provide a very good solution. The other use case is a fallback solution for the SR policy group. A fallback path may be one default policy in a SR policy group, or it's a best effort path in ISR policy group. So let's say when the traffic running, there are two kind of conditions happen. We can use fallback path. The first one, if there's no constituted ISR policy to match for the traffic, then the flow can be forwarded through the fallback path. The second, so there's no available constituted ISR policy except fallback path, then the traffic can be forwarded through the fallback path. So it provides some solution in some application scenario. So next page. That's all. And any question or comments?
Thanks, Wei Cheng. Drove?
Yeah, hi, Dhruv here. Waiting, if you can confirm, we have SR policy with composite candidate path. Are you calling what is the main difference between that and what you call as SR policy group? Is it the way that you are steering inside the SR policy? Is that the main difference?
Oh, so Chair, could you page to the second slide? I think I understand your meaning. So, Joy, could you page the page 2 of the slides? Yeah. So, in fact, I think as a policy group, in fact, represents composite candidate path, which defined in segment routing policy draft. I think I agree with you, but in the draft, it didn't give any use case or how we can use that. So here, when we deployed SR policy in our network, we found that the solution is good, but how to use it, we should give some detailed solution. So that's why we write this draft. We call that a use case draft, and hope other operators can use the best practice. That's.
But in this case, I think the biggest issue is that you are deviating from what is defined in the architecture, SR policy architecture draft, where it says that in case of composite SR policies, you will be doing load balancing based on the weights. But here, what you are proposing is that you want to do send VIP traffic on one and non-VIP traffic on another. I think that's not part of the draft. Anyway, since we are out of time, I'll take my question to the list and I'll let other people speak.
Thanks, Drew. Yeah, Mike, please go ahead.
From Cisco. Yeah, I just wanted to point out that like the unit of signaling is the candidate path. So when you say it's a special SR policy, it's really like a special SR candidate path within the policy. And second, I think, yeah, we should put something in the SR policy architecture draft about the possibility, at least, to send traffic using the DSCP or whatever else instead of or in addition to the weights. That's all for me.
Yeah, understand. In fact, for the SR policy group, I think that may be some hierarchical solution. I think that is we maybe need to define some more thing to to make it worthwhile?
No, I don't think so. I mean, because it's basically just the unit of signaling is the candidate path. Like you don't need to signal. You can have a policy with just one candidate path, right? Or you can have multiple candidate paths. So you can put a restriction that like a policy can have one candidate path if it's composite or something like that.
Yeah,
I'm gonna have to. Sorry, Wei Cheng. I'm going to interrupt here because we got 7 minutes left and one more presentation. So
okay.
to be fair to them, Guyan and Boris, you're in the queue. If you can be quick, please go ahead. Guyan first.
Yeah. Just a quick question: is this draft? I guess you mentioned like composites. Or are you? I guess seems like you're doing some type of mapping, but is this introducing something new? I guess, to the SR policy, and it sounds like it is. And if it is, I mean, I guess the concept of actually adding, I guess, addition to weights, I guess, with mapping of DSCP, would something like this, as the SR policy draft has not been, is still being developed and it's not an RFC, could some of this actually, this work be combined into the existing SR policy draft? I don't know, just a thought. Thank you.
Well, it's actually on the RFC queue, so
oh, it is.
so let's take this to the list. And Boris, unless if you can be very, very quick.
Yes, thank you, Jim. Very short question. So please update the draft with implementation status as it will be possible. Thank you.
Thanks.
Thanks.
Okay, Joel, you just pointed out to me, my laptop is showing me 9:24, but I just looked at my phone and it's 9:31. So I guess we're actually out of time.
Apologies to the circuit switched segment routing presentation, but we are out of time at this point. And so we are required to end it here. Thank you very much, everyone, for your time. Take all the discussions to the list. Thank you.
Thank you, everyone. And hopefully we'll see you all in Philadelphia.